Okay, so let's continue to develop our theory of homogeneous coordinates on the plane. This time we're going to focus mostly on showing that the standard axioms of projective geometry can be derived purely from thinking about homogeneous coordinates. So in the last part I defined homogeneous coordinates for points and lines and gave the condition when a point is upon a line, which is basically just that the dot product of the coordinates of the point and the coordinates of the line equals 0. So now I'm going to build on that to show the different axioms of projective geometry can then be established. So the first axiom is that every pair of points is connected by a line. And basically, if we have a point y and a distinct point z, then this here is the coordinates of the line that joins. So if we have a point y and a point z, this is the coordinates of the line that joins y and z. So, for example, the first entry is the determinates y2, y3, z2, z3. And if you want a reminder about determinates, 2 by 2 determinates, here's the expression for a general 2 by 2 determinant. The determinant a, b, c, d is just equal to ad take away bc. Okay, so I recommend you check that for yourself. Check that the dot product of this with y equals 0, so point y is on this line, and the dot product of z with this equals 0, so z is on this line. And once we've established this, we then get the dual results. Pretty much we just get it by the same reasoning, because points and lines basically are logically equivalent objects. So by similar reasoning we get that lines y and z, which are distinct, meet at a point, and the point basically has a very similar description to this line up here in terms of determinants. So we've got our unique line that joins any pair of points, and we've got our unique point that any pair of lines meet at. So we've got our first two axioms of projective geometry. Now let's have a look at some quadrangles. Okay then, so let's have a look at how to establish another one of the fundamental axioms of projective geometry in the plane. And that is that the diagonal triangle, in this case ABC, of a quadrangle is consisting of 3 points which are not collinear. It's a proper triangle. So here a quadrangle is defined as 4 points, no 3 of which are collinear. So we're going to be using two sort of opposing conventions now. When I'm using blue and capital letters, here I'm referring to points. And when I'm using black and lowercase letters, I'm referring to the homogeneous coordinates of points. Okay, so we want to show, given this assumption that P, Q, R and S form a quadrangle, that these diagonal points A, B and C, which are the meeting points of edges of the quadrangle which are not vertices, want to show that those 3 points are not collinear. So we'll begin by assuming that P, Q and R are not collinear. And there they are. And then we have that A is going to be another point on this line between Q and R. So we call point Q bracketed Q, that's its homogeneous coordinates. R is called bracketed R. And with A is another point on that line, so we're free to give it the coordinates Q plus R. You can go back to when I was talking about lines in the last lecture to see why that's the case. And then the next thing is we know that S is going to be a point which lines up with A, which is Q plus R, and P, which has homogeneous coordinates P. So since this is just a sort of independent point on this line, we're free to give it the simplified coordinates P plus Q plus R. And by doing so, we've assumed that it's not collinear. We're assuming that it's not forming any collinear triples either. So now we have P, Q, R and S and A, we can determine these other two diagonal points. So you can verify this for yourself, that all of these assumptions so far imply that B has to be equal to R plus P and C has to equal P plus Q. B being defined, of course, as the meet of the line through Q and S and P and R. And C, you can see how that's defined as well. So now we're going to finish the proof of this. So we have now that A, B and C are not collinear. Why? Well, we write the determinants for the vectors A, B and C, and we then compute this determinant and we can show that it's equal to 2 times the determinant we get by considering P, Q and R, which is this thing here. And we know that's non-zero by our assumption that P, Q and R are not collinear, because this is a necessary and sufficient condition for P, Q and R to not be collinear. So that basically finishes the proof. We've shown that the 3 points within a diagonal triangle are not collinear. That's one of the important axioms of projective geometry right there. So I urge you to study this, particularly how this sort of homogeneous coordinates addition works. Okay, so 2 more axioms to go. We want to, well, proving axioms sounds a bit daft, but we're proving what's normally taken as the axioms of projective geometry. Let's put it like that. So the next one is Desargues Theorem, a classic result, stating that if 2 triangles have their vertices perspective from some point, so the lines through corresponding vertices are all concurrent on this point, then the 2 triangles will be perspective from a line, in the sense that if we extend out the edges that are corresponding to one another, then they'll give us 3 points which are collinear. They're all lying on the same line. So how do we show this? Well, it's basically all here, but I need to talk you through the order of how we define these things. So we start off, we define our origin, that the triangles are perspective from, this point O. We'll give that homogeneous coordinates U. Our first triangle we shall call P, Q and R, with homogeneous coordinates P, Q and R. And our next triangle, which is perspective to the first, we'll have vertices P dash, Q dash and R dash, and we're free to assume that the homogeneous coordinates of these vertices are just equal to the homogeneous coordinates of these vertices plus this, by this idea that if we have a line through points with vectors x and y, and we have a third point on that line, we're free to call that point x plus y, because we can always choose x and y such that that works out. So we can assume without loss of generality that P dash equals U plus P, Q dash equals U plus Q, and R dash equals U plus R. Now what we're going to do is work out where these red points are. These 3 red points here, which are the points generated by the meets of corresponding edges of our triangle. So let's start out with D. We find this point D, it's the join of the edge through Q and R, and the edge through Q dash and R dash. And so you can try and convince yourself that has to have coordinates q minus r, or something proportional to that. So D has to have coordinates q minus r. Similarly, we can show that E has to have coordinates r minus p, and F has to have coordinates p minus q. So you can get that just by thinking about how you could express these points in terms of parameters. The key idea, I would say, to get this is that if you have a line through x and y, then you can parameterize that by saying the points on it are those which have the form lambda x plus y. And as you vary lambda to be any real, you get all the points on that line. So if you do that for these lines which meet to form these red points, and you solve for the parameters, you see that these are the only possibilities. And so now we have these 3 points. We want to show that they are collinear, because that will prove Desargues Theorem, prove that you have this line that the 2 triangles are perspective from. So we can do this simply by using determinates. Remember, we have this determinate condition for 3 points to be collinear. So we load the coordinates of the 3 points, D, E and F, into a determinate and compute it. And if you compute this, you'll see, that this is 0. So that shows Desargues Theorem holds. Okay, so what we're going to do now is establish the last axiom we need to show that the things we're talking about with these homogeneous coordinates satisfy all of the axioms of projective geometry. So finally, we want to, well, if we're following the work of Coxeter, technically we want to prove that the axiom saying if you have a projection from a line to itself and it has at least 3 distinct fixed points, then it has to be the identity. That's the axiom that we want to prove. But we can prove the equivalent result, which is the Fundamental Theorem of Projective Geometry. What that basically says is that if you have a projection from a range of points on a line to a range of points on a line, and you know how that projection works on 3 distinct points, so you know how the image of a point y, the image of a point z, the image of another point, we can call it y plus z. If you know the images of those 3 distinct points, then essentially you know all the information about how the projectivity works. And the whole thing is then sort of specified by that information. So we want to show that, and then the axiom I was just saying follows from that. So to do this, of course, we're going to have to talk about what projections are and how we discuss them in terms of homogeneous coordinates. Now, this treatment here is a lot neater than some of the treatments I've seen in other books on projective geometry. So a projection is a composition of elementary correspondences. An elementary correspondence is a certain kind of mapping, and a projection is another sort of mapping. We're thinking of projections here as mapping from one-dimensional forms to one-dimensional forms. By a one-dimensional form, I mean either the set of points on a line or the set of lines for a point. Okay? So a projection from such a 1D form to a 1D form is a composition of elementary correspondences. An elementary correspondence is something very simple. So we'll have a point, we can call it V, and we'll have a line, we'll call it L. And basically, we just say that every point on the line is in elementary correspondence with the line we get by joining that point to V. Okay? So this gives us a correspondence from the range of points on L to the pencil of lines through V. Okay? So for example, little y corresponds to this line big Y, which is obtained by joining little y to V, and so on. So what we want to do is to get some sort of conditions for how we can think about such an elementary correspondence working for all of the points on this line. And so what we have here is an expression for this diagram here. This symbol, this sort of triangle with a hat on top, that means is projective to. So you can read this as saying little y is projective to big Y, little z is projective to big Z, little y plus little z is projective to big Y plus big Z. In this case, the projection is a special one, an elementary correspondence. Okay, so we're going to parameterize this line L here. So we're going to refer to a general point on it, and we can do that by calling the point mu little y plus little z. So that's some general point on here, and then we want to see, well, what's the line through V that that point is going to be in elementary correspondence with. And our little theorem here, written in black, is stating that this point is in elementary correspondence with the line mu big Y plus Z. Okay, so just before I get into the proof, let's just emphasize what's going on. Y, little z, and little y plus little z, they're three distinct arbitrary points on this line L. And we're saying we know, in an arbitrary way, how these points are put into elementary correspondence with lines through V. And from that, we're getting a statement here about the image of a generic point on the line L. And we're saying we know what that point corresponds to, which line that corresponds to, and it's this. Basically using the same parameter, almost identical expression. But how do we show that this holds? Well, we're going to use this definition of when a point lies upon a line, which is when, essentially when the dot product of their homogeneous coordinates equals 0. Okay, so firstly, let's just go through this argument. This is going to help us. So when we have the line big Y plus big Z, that's obviously going to touch the point little y plus little z. So we have that the product of this and this is 0. But we can expand this out to give us some useful algebra. So expanding it out, we get that this is equal to the product of big Y and little y, plus the product of big Y little z, plus the product of big Z little y, plus the product of big Z little z. Well, we know that this is 0, because obviously the line big Y contains the point little y. Similarly, we know that this is 0, so that implies that this inside the red region is also 0. We have that big Y product little z plus big Z product little y is 0. Okay, so now we can use this to prove our little theorem here. So we want to show now that the product of mu big Y plus z and mu little y plus little z is 0. So let's expand this out using the standard algebra of dot products, and we get that this is going to be equal to mu squared times the product big Y little y. That's fine, we know that's 0, plus mu times product of big Y little z plus product big Z little y, and we know that's 0 from here, plus the product of big Z little z. Well, that's 0, of course, because point little z is on the line big Z. So we know that this is 0. So we've shown indeed that this point lies on this line. So these two entities are in elementary correspondence. So basically now we've managed to prove this result, and we've got an expression for how elementary correspondences work. Now the important thing is that you can sort of repeatedly chain this argument to basically get the same kind of statement, but something that works for any projection from a one-dimensional form to a one-dimensional form. So For example, I can draw another line up here, and then I can look at the corresponding points. So the point where the y plus z, the point that big Y plus big Z goes through, we can call it little y dash plus little z dash. And this is obviously going to be projective to this, because it's related by a sequence of elementary correspondences. And similarly, we're going to have that mu y plus z, this sort of generalized parameterized point on L, is going to correspond exactly to mu y dash plus z dash. So this parameterization is describing a point, it's also describing the thing it's projective to. And so, like, just applying this again and again, we basically get that this condition we've just shown holds, for example, when we have a projection from a range of points on a line to a pencil of lines through a point, So we can write that algebraically, that when little y is projective to big Y, little z is projective to big Z, little y plus little z is projective to big Y plus big Z, then it must be that mu little y plus little z is projective to mu big Y plus big Z. Okay? And that doesn't just hold when the range of points on the line and the pencil of lines through the point are in elementary correspondence. It works in general when they are projective to one another, because this kind of mu-based argument holds when you repeatedly apply elementary correspondences and apply this reasoning. Similarly, we have that the relationship holds when we have a projection from a range of points on a line to a range of points on a line. And therefore we have our fundamental theorem of projective geometry, because basically what we're saying here is that if we know how y, z and y plus z are mapped on a range-to-range projection, then we can use this sort of algebra here to get an expression for how a general point, mu y plus z, is mapped to its image mu y dash plus z dash. So this is telling us what's necessary, what's sufficient in order to fix the entire way a projection from a range of points to a range of points works. And what is sufficient is to know 3 points and their images. So there we have it, the fundamental theorem of projective geometry. To show that this implies Coxeter's axiom, we just say, well, if we're going to do a projection from a range of points on a line to itself, then if we know the fixed points, then that shows that mapping, that's basically specifying, if we say that mapping has 3 fixed points, then that's specifying the 3 objects and their images under the mapping. That uniquely specifies the whole projection by this fundamental theorem, and we know that the identity works like that. So the identity has those characteristics, therefore such a mapping must be the identity. That's how we prove Coxeter's axiom. But I think this fundamental theorem is a bit nicer, it's more expressive.